Again, good afternoon. I'm Sir Febus, Engineer Febus Reidj Cruz from the School of Electrical, Electronics, and Computer Engineering. Our topic for today is about basic physics of semiconductors. So the topics included in basic physics of semiconductors would be semiconductor material and p-n junction. So these are the two major topics under the basic physics of semiconductors. So for more details, you can read the chapter 2, Basic Physics of Semiconductors in our textbook, Microelectronics by Professor Razabi. And the expected outcome is at the end of this topic, we must be able to understand the characteristics of semiconductors and be able to solve problems on the basic physics of semiconductors. So on the semiconductor material, we'll present the different materials in electronics, which are conductor, insulator, and semiconductor. We'll present the different charge carriers in semiconductor. We call them free electrons and holes. Then we'll discuss the different types of semiconductors, the intrinsic, the N-type, and P-type. Then we'll have the different current in semiconductor. We have the diffusion current and the drift current. Then for the p-n junction, we'll present the structure of p-n junction. Then we'll describe the p-n junction in equilibrium. Then what happens to the p-n junction under forward bias, and what will happen to the p-n junction under reverse bias, as well as what will happen to the p-n junction under the breakdown condition. So those are the expected topics under basic physics of semiconductors. Here are the materials in electronics. So we can classify materials used in electronics according to their conductivity. So we have here a graph showing the conductivity and resistivity. So conductivity is the reciprocal of resistivity and vice versa. So the first type of material are conductors, having very high conductivity or low resistivity. Then another type would be insulators. These are materials with very low conductivity and very high resistivity. And the material in between conductors and insulators are referred as semiconductors. Examples of good conductors are single element metals. So the most conductive is silver, followed by copper, then gold, then aluminum, and then iron. And for conductors, the number of valence electrons is between 1 to 3 electrons, with 1 valence electron. Materials with 1 valence electron exhibit the highest conductivity. So silver and copper have single valence electrons. Then the energy gap, or the amount of energy to allow current flow, electrical current flow in the material, is 0 electron volt or almost 0 electron volt. So for as long as you apply a voltage source, connect a certain wire, then for sure there would be a current, electric current flowing through the closed circuit. While for the insulators, good examples of insulators are usually compound materials, so such as air, plastic, rubber, or glass. And the number of valence of insulators are from 5 to 8 electrons, with 8 electrons being completely filled are the best insulators, are the materials exhibiting best insulator characteristics. For the semiconductors, so before that, insulators, the energy gap, for example, in silicon dioxide, which is the insulator in integrated circuits, the silicon dioxide requires an energy gap of 8.9 electron volt. So insulators normally do not allow electricity except during breakdown. So pag sinobrahan mo talaga yung applied voltage, there is a tendency na mag-conduct pa rin even though it is insulator. So basta na provide mo yung required energy gap, there is a possibility na magko-conduct pa rin siya. But under normal condition, we try to avoid insulators conducting electricity, no? Kasi normally ang purpose nga nila is to prevent any current. Now for the semiconductors, these are available in elements as well as compounds. So the most common elemental semiconductors are the silicon and germanium, while the most common compound semiconductors are the gallium compounds. So we have the gallium arsenide and the gallium phosphide. And the number of valence of semiconductor materials are 4 electrons. So it is in between that of conductors and insulators. So the energy gap is also in between. So for silicon, the energy gap is 1.12 electron volt. So again, energy gap is the amount of energy needed to be applied on the single electron to have electrical current. Okay, so is it clear so far? Please confirm.
Yes, sir.
Yes, sir.
Okay, so
Yes,
review
sir.
lang naman to, no? So these are fundamental or basic descriptions natin. But nevertheless, i-present ko pa rin so that we will have same understanding ng mga terminologies and concepts. So allow me to present the silicon atom using the planetary structure or the Bohr model. So silicon is the most widely used semiconductor material, and the atomic number is 14, which means on the nucleus, there are 14 positive protons. And to distribute the number of electrons, we have this equation. Ne is the maximum number of electrons in a shell, and it is equal to 2 times the square of N, where N is the shell number. So for the first shell or the K shell, the maximum number of electrons would be 2 times 1 squared, or the maximum number would be 2 electrons. On the second shell or the L shell, you have 2 times 2 squared. The maximum number of electrons would be 8, up to 8 electrons. So at this point, you now have 14 protons and 10 negative electrons. So the next shell would now be the valence or the outermost. So that would be shell 3 or M shell, having the remaining 4 electrons. So silicon atom has 4 valence electrons. And as we all know, valence electrons are the only electrons contributing to electricity. So what we are going to do is we are going to group together the bound or the inner electrons together with the protons and represent all of them as a core. So you have 14 positive protons together with 2 bound electrons in K shell and 8 bound electrons in L shell for a net charge of positive 4. So the positive 4 core again represents the protons in the nucleus and the bound electrons. And surrounding this core, we have the valence having 4 valence electrons. So the charge would be negative 4. So this will now be our representation for the silicon atom. We can draw a core with plus 4 and surround it with valence electron with valence shell with 4 negative electrons. So the model will still be neutral. All right, so this will now be our representation or illustration for our silicon atom. Henceforth, no? Going forward, ganito na lang yung magiging drawing natin. Now for the silicon crystal, so if you have a silicon atom, and then in a crystal, it means that you have thousands or even millions of silicon atoms. So when you say crystal, this is the material comprised of many silicon atoms. And for the silicon crystal, the silicon atoms exhibit what we call covalent bonding. So each of the silicon atom will share its valence electron with its neighbor atom. So the single silicon atom with 4 valence electron will share each of its valence with 4 other neighboring atoms. So magiging ganito yung itsura niya, no? Inside the silicon crystal, the silicon atom will have a completely filled valence shell. So magiging 8 na siya bale, no? So yung the other silicon atom will also have ang assumption natin, all of the silicon atoms will be completely filled with the assumption na lahat sila may katabing neighboring silicon atoms. Okay? So except yung mga nasa edges na, no? Yun na lang yung hindi completely filled. But ang assumption, all of the silicon atom inside the silicon crystal will have a valence shell that is completely filled with 8 valence electrons. So the silicon atom in crystal structure will now have 8 valence electrons. Now, we will have a situation here. Based on our introduction, we said that insulators are materials with 8 valence electrons. So silicon in a crystal structure will exhibit insulator properties. So this will not be useful for semiconductor devices. So since it will act like a perfect insulator. Okay? So hindi siya pwedeng gamitin hindi pa siya pwedeng gamitin as a semiconductive material. Okay? So eventually we need to modify the conductivity of silicon materials. So we have different types of semiconductors. 2 major categories. We have the intrinsic semiconductors. These are the pure materials. So for example, purely silicon materials. And we have the extrinsic semiconductor materials. So these are intrinsic semiconductor that undergo the doping process that has been added with other elements. Kaya ang tawag sa kanya dope. So meron ng minix or hinalo na elements. Okay? So for the intrinsic, it could be elemental or compound or intermetal ang term natin. While for the extrinsic, it can be negative type or simply N-type or a positive type or P-type. So the overall, we can say the basic types of semiconductors would be intrinsic, N-type, and P-type. Okay, so clear ba so far? Please confirm.
Yes, sir.
Yes, sir.
All right, sige, thank you. So that ends our description for materials in electronics. So let us proceed to the charge carriers in semiconductors. So what do you mean by charge carriers and how they produce current in semiconductive materials? So charge carriers in semiconductor. So for example, we have the silicon atom in a silicon crystal having 8 valence electrons. If one of the valence electron absorbs additional energy the energy level of that valence electron will increase and will eventually become a free electron. So as the valence electron escapes, as a free electron, it will leave a vacancy in the valence orbit. So the vacant space in semiconductors is, we call it as a hole in semiconductor. So because of this absorption of additional energy, the valence electron will become free electron and hole pair. Nasundan ba yon, yung concept na yon?
Yes, sir.
All right, sige, thank you. So this is the process we call generation. So this is the generation of charge carriers, which are actually the free electrons and holes. And when the free electron moves, it will use the energy, and eventually the energy level will reduce, and eventually that free electron will have the energy level the same with the valence. So eventually the free electron will go back to that vacant space. It may not be the original hole, but the free electron may occupy another vacant space. And after that, the free electron will once again become valence electron. So this is the process we call recombination. Okay, so this is the process wherein the free electron will occupy a vacant hole and it will go back as a valence electron. Now we have the so-called density of carriers in silicon. So this describes how many carriers. So again, sir, ano ba yung carriers? Carriers pertain to the free electrons, number of free electrons, or the number of holes. In pure semiconductors, the number of free electrons is equal to the number of holes. Since every time you create a free electron, we also create the same number of holes. All right, so carriers, again, pertains to the number of free electrons and to the number of holes. And in pure semiconductors, the number of free electrons is equal to the number of holes. Now, when you say density of carriers, this describes the number of carriers for a given volume of silicon, for a given volume of semiconductor material. And this can be computed using this equation. So the density of carriers intrinsic, so it means it is pure semicon, no? The density of carriers of intrinsic silicon is equal to 5.2 times 10 raised to 15 multiplied by the temperature in Kelvin raised to 1.5 times the exponential of the negative of energy gap divided by 2 times K times T. So ito yung equation natin, paki-take note, no? Again, nasa chapter 2 rin naman yan, no? So i-copyahin nyo yung formula. So Ni is the density or concentration of carriers per unit volume of silicon. So it describes the number of carriers per cubic centimeter of silicon. And then T is the temperature in Kelvin. So if the temperature is in Celsius, add 273 to convert to Kelvin. Then Eg is the band gap energy, or this is the energy gap. For silicon, the energy gap is 1.12 electron volt. And to convert that to joules, conversion is 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And K is the Boltzmann constant, equal to 1.38 times 10 to the negative 23 joules per Kelvin. All right? Nasundan yung formula?
Yes po.
Sir.
Yes. Nasundan?
Yes po, sir.
Okay, sige, thank you. Now we have here the effect of temperature in carrier density. So based on this equation or model, you have the temperature raised to 1.5, and then you have the inverse, the exponential of the inverse of the temperature. So the overall effect of that temperature is as the temperature increases. So I plotted the temperature in Celsius. So from 0 degrees Celsius to 100 degrees Celsius, the carrier density, somehow we can see it exponentially increases. No? So hindi siya linear, but the number of carriers increases with the temperature. So it means whenever you have an electronic device made of semiconductive material, as the temperature increases, we expect that the number of electrons that can become electrical current is increasing. So habang umiinit, dumadami yung electrons sa semiconductors. So yung current doon, pataas ng pataas. There is a possibility na tataas yung kuryente natin. Okay? Lalo pag naka-turn on and even kapag naka-turn off. Pag naka-off yung devices, there is what we call leakage current. So in both cases, basta uminit, tumaas yung temperature, based on this, we can see that the number of electrons will increase. So that is why, if you observe most of the electronic devices, it is advisable na gamitin natin sila sa normal temperatures. So hanggang maaari wag mong ibilad sa araw, di ba? Or kung kayang naka-aircon yung computer, mas maganda. Okay? So to avoid yung continuing increase in the carriers. So eventually mag-overheat kasi yan kapag masyadong mataas. Alright, so in this example, if you get temperature at 27 degrees Celsius or that is 300 Kelvin, the computed intrinsic carrier density of silicon is 1.08 times 10 to the 10 carriers per cubic centimeter. Okay? So try to use the formula if you can get the same value. Okay? Now, again, the silicon atom in a silicon crystal. So we already know that we have the carriers, which are the free electrons and the holes. So how do we transport free electrons in semiconductors? So to transport the free electron along the material, we have to apply voltage. So for example, we apply positive voltage on the left side and negative voltage on the right side. Then by principle of Coulomb's law, negative free electrons will be attracted towards positive voltage. So the free electron will flow towards the positive voltage. It will flow towards or going to the left. And that movement of free electron is what we call electron current. Okay? So electron current refers to the flow of free electrons. Now, next question. How do we transport holes in semiconductor? Again, when we say hole, this is just a vacant space in the valence shell. So paano gagalaw yung vacant space, no? So since walang particle talaga yan, so hindi siya yung mismong gagalaw. So let's say at time equal to 0, again we connect positive voltage on the left side, negative voltage on the right side. So what will happen is, so since hole is just a vacant space, the actual particle that will move will be the negative valence electron. So valence electron is negative. It will be attracted towards the positive voltage. And since there is a vacant space, the valence electron will occupy that vacant space. So at time equal to T2, eventually the valence electron already occupied the previous location of the hole. So effectively, the hole will now be on this location. So effectively, the hole moves going to the right from this initial position going to this new location. So as if the hole is moving towards the negative voltage. So that is why holes in semiconductors are described to be positively charged, since effectively they are flowing towards the negative voltage. But in actual, it is actually the valence electrons moving towards the positive voltages. Naintindihan ba?
Yes po, sir.
Yes, sir.
Alright, sige, thank you. So at time equal to T3, we have another valence electron. Since it has a neighboring vacant space, the negative valence will again be attracted towards the positive. So after a while, the valence electron will now occupy this previous position of the hole, and the hole eventually moves again towards the negative. And last one, another valence electron will move towards the positive, and the hole again effectively moves going to the negative. So the movement of holes going to the negative due to the movement of the valence electrons is what we call hole current in semiconductor material. Okay? So note that hole current is actually the flow of valence electrons along the valence shells from one atom to another atom, moving from one vacant space or vacant hole to another vacant hole. Okay? So ganun yung trabaho ng holes. So pag mas marami yung holes, mas maraming valence electron ang pwedeng gumalaw. No? So eventually, hole current increases. Alright, so the transport of carriers in semiconductor are made of either electron current and hole current, or I would say are comprised of two currents, yung electron current and hole current. And this transport of carriers will have two mechanisms. The first one is the drift current. This is the amount of current in response to the applied voltage or its electric field. So the drift current of electron current and hole current is directly proportional to the electric field. And another mechanism or another type is the diffusion current. So this pertains to the movement of charge carriers in the semiconductor material due to the concentration gradient. So we expect a movement of carriers. So that is the diffusion current, and it depends on the concentration gradient. All right, so changes in the concentration N along the length of the semiconductive material. Okay, so dalawang components yan. No? You have drift current, dalawa yan, electron current and hole current. So basta may voltage, you'll have drift current. And another component or mechanism, you have the diffusion current. Whenever there is concentration gradient, electron and hole can have movement or what we call diffusion current. Naintindihan ba to? Please confirm.
Yes, sir.
Yes po, sir.
Sige, thank you. All right, that ends our description for the charge carriers in semiconductors. So let us continue on the types of semiconductors. So again, these are intrinsic, N-type, and the P-type. So again, semiconductors are either intrinsic or extrinsic. Under the intrinsic, it's either elements or compound. And under the extrinsic, it's either N-type or negative type or positive type or P-type. Now for the intrinsic semiconductors, again, these are pure semiconductors. And because of completely filled valence, pure semiconductors exhibit very low conductivity. So yun yung pinaka-problem sa kanya, no? And they have equal number of free electrons and number of holes. So we are going to denote number of free electrons using letter N and the number of holes using letter P. So N for negative, P for positive holes. So for the intrinsic semiconductors, the carrier density of intrinsic or pure semiconductor is equal to the number of free electrons and is also equal to the number of holes. So we can write this description for the intrinsic semiconductors. Ni squared, the square of the intrinsic concentration, is equal to the product of free electron concentration times hole concentration. And we have here the examples of intrinsic semiconductors. So let me show you the portion of the periodic table with elements used in semiconductor manufacturing. So under group 2B, you have zinc and cadmium. Group 3A, you have boron, aluminum, gallium, indium, and thallium. Under group 4A, you have carbon, silicon, germanium, tin, and lead. Group 5A, we have nitrogen, phosphorus, arsenic, antimony, and bismuth. And group 6A, you have oxygen, sulfur, selenium, tellurium, and polonium. So these are the elements used in semiconductor manufacturing. Now, for examples of elemental intrinsic semiconductors, these are the elements under group 4. So technically, all of the elements are semiconductors since they all have 4 valence electrons. But the practical semiconductors are the silicon and the germanium. All right? So silicon and germanium. Carbon, having very small atomic size, is more of an insulator. While tin and lead, though technically are semiconductors, but because of large atomic sizes, they behave more of conductors. Okay? So again, practical examples are the silicon and germanium. Then for the compound and the intermetal, we have several examples. What we need to combine is the elements that will produce a stable compound, a compound with 8 valence electrons. So we can mix group 3A with group 4A. So you can have boron mixed with phosphorus, mixed with arsenic, antimony, and bismuth. So you have boron phosphide, boron arsenide, and so on. So pwede mo siyang i-matrix. Alright? Similarly, you can have the aluminum compounds. No? I-matrix mo rin dito. Likewise, you have the gallium. So gallium are the most popular since these are the materials used in light-emitting diodes. Yung mga LED natin, yung mga LED display, most of them are made or fabricated using gallium compounds. Alright, so i-matrix mo lang dyan. As well as the indium compounds. Okay? Then other examples, group 2 mixed with group 6 will give us 8 valence. So you can have the zinc sulfide and zinc selenide, as well as with the cadmium compounds. And then other example, we can also mix group 4 with another group 4. So we have the compound silicon carbide as well as the silicon germanide. Okay, so pag tinanong kayo, give examples of intrinsic semicon. So you are no longer limited with silicon. No? So from here, makita natin we have many examples. Okay, nasusundan ba? Please confirm.
Yes, sir.
Yes po, sir.
Sige. Alright, so for the N-type semiconductor, so semiconductor added, N-type semiconductor is a semiconductor added with a controlled amount of donor atoms, resulting in greater number of free electrons than the number of holes. So you have more number of negative electrons than positive holes. So that's why the characteristic is referred as negative type or simply N-type. So to illustrate doping through the process of diffusion. So let's say this is our pure or intrinsic silicon material. We are going to place the silicon wafer or silicon material in a furnace or oven, subjecting it to a very high temperature. So the surface of the silicon wafer will melt, or in atomic level, we can say that the covalent bonding are separating from one atom with another atom. So lumuluwag, no? Kumakalas yung covalent bonding natin. And during this situation where silicon atoms are detached from one another, this is the moment we are going to introduce a dopant. So in this example, we have a phosphorus atom, phosphorus dopant. Each of the silicon, if you notice, has 4 valence electrons. And we are going to introduce a phosphorus dopant with 5 valence electrons. So during high temperature, we expose the silicon to phosphorus gas and allow the phosphorus to naturally penetrate the silicon material. So that is the process of diffusion. Then after some time, so aside from the phosphorus, other examples of group 5 or pentavalent atoms are the arsenic, antimony, and bismuth. But usually, we use the phosphorus dopant since it is the smallest among the 4. So madali siyang i-diffuse, no? Madaling pumasok. Okay, so kahit konti lang yung space, it can easily penetrate the silicon material. And after some time, we allow the material to cool down or crystallize. So within the silicon atoms, we'll have the phosphorus atom. And again, since it has pentavalent, it will have covalent bonding with 4 neighboring silicon atom. And the 5th valence will be free electron. All right? So just imagine if you introduce 1 million phosphorus atoms, you'll have 1 million phosphorus atoms with this kind of structure, with each of the phosphorus atom having an excess free electron. So unlike in the process of generation, pag naglagay ka ng free electron, merong hole. But under the doping process, you can produce free electron without any hole pair. So yun yung trabaho ng doping natin. Okay? So to sum up, an N-type semiconductor is manufactured by adding intrinsic or group 4 materials with group 5 elements. So this would result to a material with 8 valence. Ito yung maximum number of valence natin. So the excess will become a free electron. So that's why we call it negative type or N-type. So we denote the concentration of donor atoms. So those are the pentavalent, donating an excess of free electrons. So that's why ang tawag donor atoms. So we denote the concentration of donor atoms as N sub D. And this will dictate the number of free electrons. So N will be equal to the concentration of donor atoms. So if we apply the intrinsic formula, the amount of holes in the N-type can be computed using Ni squared divided by the donor concentration. All right, so can you follow? Please confirm.
Yes, sir.
Yes po, sir.
Yes, sir.
Sige, thank you. Alright, so ito yung pinaka-summary or description natin. No? For an N-type, we expect that the number of free electrons will be more than the number of holes, making it negative type or N-type material. Now for the P-type, this is a semiconductor added with a controlled amount of acceptor atoms. That results in greater number of holes than the number of free electrons. So to illustrate the doping process by diffusion, again, you have the pure silicon material. subjected to a very high temperature environment. And while the covalent bonding are removed between the silicon atoms, we are going to introduce a dopant. So this time we are going to use the boron, a trivalent atom, an atom with 3 valence. So other examples of trivalent atoms are aluminum, gallium, and indium. The most usual dopant is the boron atom, again, since it is the smallest of all the available trivalent atoms. So we can easily perform the diffusion process. So after some time, the boron will uniformly diffuse through the silicon material, and we allow it to cool down or solidify or crystallize. So when a trivalent atom bonded with the silicon material, the 3 valence will covalently bond with 3 neighboring silicon. While on the 4th neighboring silicon, there would be a vacant space. So that produces the hole. So every boron atom will produce a hole that can accept valence electron to move from one valence orbit to the other valence orbit. So that's why we call the boron or the trivalent atoms as acceptor atoms. Okay? So to produce P-type semiconductor, we mix the intrinsic, those are group 4, with group 3. So this results to a material with 7 valence with 1 vacancy or 1 hole. So again, hole are characterized to be positive. So we can describe the material to be P-type material. So the concentration of acceptor atoms are denoted as Na, and that will determine the number of holes. If you want to know the number of electrons in P-type, we use again the intrinsic equation. So N is Ni squared over Na. And we expect that the number of holes will be greater than the number of free electrons. All right? Please confirm kung naintindihan.
Yes,
Yes,
po,
sir.
All right. Sige. Thank you. So we have here the effect of doping in carrier density. So carrier density in intrinsic semiconductor, number of free electrons equals the number of holes, and they equal the intrinsic carrier density. All right, so this is our guide formula. Square of intrinsic concentration is equal to the product of free electrons and holes. And for silicon, this is our equation to describe the intrinsic carrier density of intrinsic silicon. So again, at room temperature, 300 Kelvin, the intrinsic carrier density is 1.08 times 10 to the 10 carrier per cubic centimeter. Now, when we do the doping, the carrier density in N-type, the free electrons will now be determined by the donor doping concentration. And the number of free electrons will be greater than the number of holes. So the number of holes can be calculated using this equation. And as for the P-type, the number of holes will be determined by the acceptor concentration. And the number of free electrons in P-type can be computed using this equation. And the number of holes is more than the number of free electrons for P-type. All right, so that ends our description for the types of semiconductors. All right, so let's continue with the current in semiconductors. This pertains to the drift current and diffusion current. So transport of carriers in semiconductors. So we have the electron current and hole current. They can be transported using drift current. So this is the current in response to applied voltage or electric field. Or they can be transported using diffusion current. This is the movement of charge carriers attributed to the concentration gradient. So for the electron drift current, so again, when you say drift, you have an applied voltage. So for the free electron will move towards the positive voltage. So if we have a given material of certain length and area, the electron drift current can be calculated using this equation. You have mobility of electrons multiplied by the electric field multiplied by the cross-section area of semiconductor material multiplied by the density of electrons, carrier density of electrons or concentration of electrons multiplied by the charge of electron. So IN drift is the electron drift current in coulomb per second or amperes. Mu n is the mobility of electrons. For the silicon, if not given, we can use this default value. Mobility of electrons in silicon material is 1,350 square centimeter per volt second. E is the electric field, which is the voltage divided by the length. So we can express the electric field in terms of volts per centimeter. A is the cross-section area. We can express it in terms of squared centimeter. N is the density of electrons. We can express it in terms of electrons per cubic centimeter. And then Q would be the charge of one electron. And it is equal to 1.6 times 10 to the negative 19 coulomb. Then for the hole drift current, this time holes will move towards the negative voltage. So we are going to use the same format for the drift current, except that we are going to use the mobility of holes, the hole concentration, and the rest would be the same. So IP drift is the hole drift current, again in coulomb per second or amperes. Mu P is the mobility of holes. Again, if not given, we can use this default mobility of holes in silicon, which is 480 square centimeter per volt second. E would be the electric field in volt per centimeter. A is the cross-section area in square centimeter. P would be the density of holes in hole per cubic centimeter, and Q would be the charge of hole. So the charge of hole will be the same as the charge of electron. So we are going to use the same constant, 1.6 times 10 to the negative 19 coulomb. All right, so is this clear so far?
Yes, sir.
Yes, sir.
All right, sige. Thank you. Let's continue. So drift current, the total drift current in semiconductor would be the sum of the electron drift plus the hole drift. Okay? So again, drift current is the amount of current in response to the applied voltage or its electric field. So if we substitute the formula, the total drift current in semiconductor would be mobility of electrons times electron concentration plus mobility of holes times hole concentration, all multiplied by electric field times cross-section area times the charge of electron or hole. All right, so take note, the constant. So if not provided, mobility of electrons is 1,350 square centimeter per volt second. And the hole mobility is 480 square centimeter per volt second. Now we have the drift velocity. So how fast would be the drift current? So that is what we call drift velocity. So drift velocity of carriers in semiconductors. So velocity pertains to the speed of carriers moving in a current under an electric field. So gaano siya kabilis umandar, no? So the equation is velocity is equal to mobility times electric field. And we can also express velocity in terms of mu sub O over 1 plus mu sub O over saturation velocity multiplied by electric field, all multiplied by the electric field. So V is the velocity of carriers in centimeter per second. Mu sub O is the low field mobility. This is the mobility under low electric field in cm square per volt second. So that would be the 1,350 cm squared per volt second for electrons. VSAT is the velocity saturation in cm per second. For silicon, the saturation velocity would be 10 million centimeter per second. And E is the electric field in volts per centimeter. All right, so paki-take note yung formula describing the speed of drift current. Okay, so or what we call drift velocity. So I try to plot a graph showing the velocity of carriers. So at a lower electric field, we can see that the velocity is directly related, directly affected by the electric field until we reach a certain saturation point. So yung saturation point natin kanina, we said it is around 10 million. So just above the 9.9, no? Somewhere here, the carriers will reach a saturation velocity. That even though we increase the electric field, the effect on the velocity would become minimal. So tumataas siya pero hindi na ganun kalaki as compared under the small electric field. So under high electric field, there would be some saturation. The concept is at very high electric field, nagiging chaotic na yung charges natin. No? So kumbaga, hindi lahat sila bumibilis, no? There is a possibility or probability na nagko-collide na sila with one another. So ang result nun, bumabagal yung speed nila. Okay? Kumbaga parang stampede. Instead na normal lang na tumatakbo lahat, pag nag-panic mode, sobrang bilis, there is a possibility of stampede na ang eventually babagal pa as a result, no? So, ganun yung concept natin dito. Okay? So, at this point, at an electric field of 1 megavolt or 1 million volt per cm, the computed velocity is 9.93 times 10 to the 6 centimeter per second. Ayan, can you imagine, di ba? For every second, 9.93 million centimeter yung speed ng electron. So ganun kabilis ang movement natin, no? Inside a semiconductor material. So in a blink of an eye, tapos agad ang operation ng semiconductor devices natin, no? Since in integrated circuits, semiconductor devices normally nasa micrometers lang yan. So can you imagine gaano kabilis yung movement ng electrons? Then another type of current in semiconductor is the diffusion current. So total diffusion current would be the diffusion of electrons plus diffusion of holes. And it can be expressed using this. Diffusion constant of electrons times the electron concentration gradient minus diffusion constant of holes multiplied by the hole concentration gradient times area times Q. So diffusion current pertains to the movement of charge carriers towards regions of low concentration. So I diffusion is the diffusion current. D is the diffusion constant. So this is the diffusion constant of electron, that is 34 cm square per second. And dP would be the diffusion constant of hole equal to 12 square centimeter per second. Paki-take note nyo yung mga constants natin. dN over dx is the free electron concentration gradient. Unit is electrons per cm raised to 4. And dP over dx is the whole concentration gradient in terms of holes per cm raised to 4. A would be the cross-section area of semiconductor material in cm square. And Q would be the charge of electron or hole equal to 1.6 times 10 to the negative 19 coulomb. So overall, pag tinanong tayo, then what is the total current in semiconductor? It would be the sum of drift current and diffusion current. So this will be the total current in the semiconductor material. And we can also express in terms of current density. So that is the amount of current for a given cross-section area. Pwede rin yun. And based on the diffusion constant, we also have the so-called Einstein relation. You have here the electron diffusion over the mobility of electron is equal to the whole diffusion over the mobility of electron equal to the thermal voltage, which is kT over Q. All right, so again, these are the diffusion constants. These are the mobility of carriers. And T would be the temperature in Kelvin. K would be the Boltzmann constant, and Q would be the charge of carrier. Okay. So that ends our discussion on the current in semiconductor.